Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on group, lecture number 63, in which I will discuss on complexes of a group. Let G be a group with given binary operation and H be a non-empty subset of G. H is a non-empty subset of G. Group G. Then this non-empty subset H is called a complex of group G. Now we write the definition of complex of a group. Any non-empty subset H of a group G is called a complex of a group G. Now we define multiplication of complexes. Let G with given binary operation be a group. H and K be two complexes of group G. Then multiplication of H and K is denoted by HK and defined by HK equal to X belongs to G such that X equal to small h small k. Small h belongs to capital H and small k belongs to capital K. Since elements of HK be elements of group G, therefore it is obvious that HK is a subset of group G. Since H and K are non-empty subset of group G, therefore HK is non-empty. Hence HK is a complex of group G. Now we define inverse of a complex. Let H be a complex of a group G. Then the inverse of complex H is denoted by H inverse and defined as H inverse equal to a set containing elements small h inverse belongs to G such that small h belongs to complex H. Now we prove a theorem. Theorem is if H and K be two complexes of a group G, then HK whole inverse equal to K inverse H inverse. Now we prove this. Given that H and K be two complexes of a group G, let X belongs to H K whole inverse. This is number one. Implies that X equal to small h small k whole inverse. Small h belongs to capital H and small k belongs to capital K, complex K, equal to K inverse H inverse. This belongs to capital K inverse capital H inverse. This is number 2. Therefore, from 1 and 2, we get X belongs to capital H capital K whole inverse implies that X belongs to capital K inverse capital H inverse implies that HK whole inverse is subset of K inverse H inverse. This is number 3. Now let Y belongs to capital K inverse capital H inverse. This is number 4. Therefore, Y equal to small k inverse small h inverse. K belongs to capital K, H belongs to capital H. This equal to HK whole inverse, and this HK whole inverse belongs to capital H capital K whole inverse. This is number 5. From 4 and 5, we get Y belongs to capital K inverse H inverse implies that Y belongs to H capital K whole inverse. implies that capital K inverse H inverse is subset of H K whole inverse. This is number 6. From theory and 6, we get here HK whole inverse is subset of K inverse H inverse, and here K inverse H inverse is subset of HK whole inverse. Therefore, they are equal. Therefore, HK whole inverse equal to K inverse H inverse. Proved. Now we prove the next theorem. Prove that the multiplication of complexes of a group holds associative law. Now we prove this. Let capital H, capital K and capital L are three complexes of a group G. Let HK L belongs to capital H, capital K, capital L. Here H belongs to capital H, K belongs to capital K, and L belongs to capital L. This is number 1. Since HKL equal to HKL, since HKL belong to group G and associative law holds in G, and this belongs to H K L. This is number 2. From 1 and 2, we get under bracket HKL belongs to under bracket HK, and here L implies that under bracket HKL belongs to H under bracket KL, implies that under bracket HKL is subset of H under bracket KL. This is number 3. Now HKL belongs to capital H, capital K, capital L. This is number 4. Since H under bracket KL equal to HK under bracket L, since HKL belongs to group G and associative law holds in G, and this belongs to capital H, capital K under bracket and L. This is number 5. From 4 and 5 we get H under bracket KL belongs to capital H under bracket KL implies that H under bracket KL belongs to under bracket H K and here L implies that H under bracket KL is subset of under bracket HKL. This is number 6. From 3 and 6 we get H under bracket KL equal to under bracket H KL. Therefore, associative law holds for the multiplication of complexes. Proved. Now we prove a theorem. Theorem is if H is a subgroup of a group G, then H inverse equal to H. Now we prove this. Given that H is a subgroup of a group G, let small h inverse belongs to capital H inverse. This is number 1. Implies that H belongs to H, subgroup H, and since H is a subgroup of group G, then small h belongs to subgroup H implies that H inverse belongs to subgroup H. This is number 2. From 1 and 2 we get here H inverse belongs to capital H inverse implies that H inverse belongs to capital H. H inverse belongs to capital H inverse implies that H inverse belongs to capital H. Implies that capital H inverse is the subset of capital H. This is number 3. Now, let small h belongs to capital H. This is number 4. implies that H inverse belongs to H, since H is a subgroup of group G, hence inverse exists in capital H, implies that H inverse whole inverse belongs to H inverse, and H inverse whole inverse means H belongs to H inverse. This is number 5. From 4 and 5 we get small h belongs to capital H, implies that small h belongs to capital H inverse, implies that H is subset of H inverse. This is number 6. From 3 and 6 we get H equal to H inverse. Therefore, if H is a subgroup of group G, then H equal to H inverse. Proved. Now we prove the next theorem. If H is a subgroup of a group G, then H inverse equal to H. Now we prove this. Proof. Given that H is a subgroup of group G, let AB inverse belongs to H inverse. Let this is number 1, implies that A belongs to H, B inverse belongs to H inverse, implies that A belongs to H, and here B inverse belongs to H inverse, implies that B belongs to H. Let this is number 2. Since H is a subgroup of group G, then from 2 A belongs to H, B belongs to H, implies that AB inverse belongs to H. This is number 3. From 1 and 3 we get, in 1 AB inverse belongs to H inverse, here AB inverse belongs to H, AB inverse belongs to H inverse, implies that AB inverse belongs to H, implies that H inverse is subset of H. This is number 4. Now let small h belongs to subgroup H, and since identity element E belongs to H, implies that E inverse belongs to H inverse. E inverse means E belongs to H inverse. This is number 5 and this is number 6. Therefore, from 5 and 6 we get HE belongs to H inverse, implies that H belongs to H inverse. This is number 7. From 5 and 7 we get small h belongs to capital H, implies that small h belongs to capital H inverse, implies that capital H is subset of H inverse. This is number 8. From 4 and 8 we get, in 4 H inverse is subset of H, and in 8 H is subset of H inverse. Therefore H inverse equal to H. Therefore, if H is a subgroup of a group G, then H inverse equal to H. Proved. Now we prove a theorem. Theorem is H be a complex of a group G, and if H inverse equal to H, then H is a subgroup of G. Now we prove this. Given that H be a complex of group G such that H inverse equal to H. This is number 1. Let small a small b belong to H, implies that A belongs to H, B inverse belongs to H inverse, implies that AB inverse belongs to H inverse, implies that AB inverse belongs to H inverse equal to H. Using 1. Therefore, AB belong to H implies that AB inverse belongs to H. Hence, H is a subgroup of G. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.